Now we're going to move on to chapter 5. So multiple DTR. So I'm going to move on using use this example to illustrate the idea. So acute leukemia. In the baseline, we observe XI, which include age. This is kind of a simple illustration, but hopefully that will give some idea. So age and white blood cell. So leukemia is like lacking the white blood cell, right? In your blood, white blood cell supposed to fight with diseases, right? And if that is very lacking, then you are in trouble, which actually becomes acute leukemia. Anyway, so I don't know much about this details, but now suppose we use this one to determine, and then use that to take the option. So this is maybe a doctor, right? Medical doctor give you some prescription. So under that situation, you give he or she give a C2, or otherwise give a C1, something like that. And then that is the at decision 1. So decision 1 means at time, at the first visit, right? Doctor's visit. And then next visit is a decision 2. Okay. So during that time, there's something going on, right? So then this additional information. So basically this is a covariate, but the covariate is time dependent, right? Covariate changes over time. So then WBC will change, right? Will be subscript 2. So this is kind of a simple, I do it I program it myself by using ChatGPT. So if I ask ChatGPT this kind of question, amazing. So that is very nice.
I also tried last weekend. Doing the same.
I see. So I don't need the RA for that anymore. I used to ask Yonghyun, but I'm not anymore. Anyway, so accrued information. So one thing is that, okay, so this is the interesting part, because even though doctor gives you some prescription, right? The patient does not always follow the instruction, right? So then actually you may have two different, right, result based on the response of the patient. So this is a kind of maintenance option. So follows, then you have some good treatment. So that means you can just do make sure that you are in the right level. So this is kind of maintenance. This is more like a survivor. It's more serious because you didn't really follow. Okay, so then you have basically this kind of a decision rule. So depends on the status of the patient. The doctor may give a different set of options. Okay, so that becomes a very interesting decision rule, because it's kind of a interactive, right, decision. So that's basically the idea. So then the treatment regime depends on history. So now I'm going to introduce another notation, H. So H is the history at time K. Okay, so that includes the auxiliary variable as well as the previous decision, right? The option that has been taken. So that is kind of idea. So then in the high level, we can describe it as a K decision point or stages, and baseline information is X1, and then intermediate information at K. so that is between a decision k minus 1 and k, right? You basically have 1, 2, 3. So at time 1, right, you have x1 observed. So at time 2, you will have x2 observed, of course, but this x2 is actually occurred, right? Something realized between these two time periods. So that's the kind of concept. And then treatment option. So this is a set of possible options, right? Script A is a set of possible options, while this is an element, right, in the set, in the option set. And then the history is H1, we have only one history, right? But HK, basically we have pairs of the X and A. So X, so this is time 1 and time K minus 1, right? So we have previously we have X and A, and then at the case visit, right? Case visit, we have XK observed. So then decision rule refers to the function of history. Basically, decision rule is a function of history, but it maps to A. So this is a set of history, right? Possible histories. And this is the set of the options so that is a decision. And then treatment regime is basically a vector of the sequence of rules, right? Sequence of rules over time based on the history. So that's quite complicated, I'd say. But anyway, so let's use some simplification of the notation. So overbar notation will be used to the time, right? The vector, but up to time k. So x bar k is a vector. So auxiliary variable, all the auxiliary variable up to k, right? This is ak, the same story, right? A bar k is all the a up to k. And then this is the kind of set, possible set. And then we'll use capital K to denote the final, right? Final, last time. And so then when we reach to the capital K, so when we reach to the final digit, then we don't need, sometimes we can ignore the subscript K, capital K, same here. Okay. So then in terms of for history, so at time K, the history is all the auxiliary variable up to K, right? And all the options that was taken up to K minus 1, right? So that's why we have a K here, but we have a K minus 1 at A. Okay. And then finally, so finally we have a overlap. dk means the decision rule up to k. Okay. So so we can write the rules recursively. So so at decision time 1, it's just simple, right? You just use the initial baseline information. But decision 2, so decision is based on history at 2. So at decision at 2 has a 2 component. One is the auxiliary information. The other one is the options taken so far, right? So that is basically this way. Okay. So we have a recursive way of defining the decisions, right?
So basically, A1 is equal to D1 X1.
So right, but the notation, right? D1 is a function that maps to A.
Right.
So D is the function that maps to A. So for me, right, for the agent, we choose D.
Right.
But so right.
But as a particular patient, the action is the same as the decision that the agent suggested.
Right, but that's the realized one. But we are interested in comparing over different decision.
Right.
So then that becomes a potential outcome concept, because we just have the realized one in the data, but we are interested in understanding what would be the outcome, potential outcome for other options, right?
Right. So the realized one may not be the optimal.
Right. That's right. Yes. So yeah.
Jay,
Yeah.
if you go back to the beginning of the example, so there should be not the case of the agent. So the doctor suggested a decision and the patient didn't follow. It's kind of still all the patients should be comply to the doctor's suggestion, right?
In theory, yes, but in reality, no.
Right. Because if there is a non-compliance, it's not missing at random.
I see. Right. Yeah.
Right,
So this, right.
Reality, yes.
You're right. So I think the concept here is that X2. So I guess the concept here is X2 contains the response status.
The response status of the previous.
Right.
Previous.
Yeah. So this is a part of your X2.
Right.
Okay.
Right. Yes, but if you think about whether it is unconfounded at X2, then we basically need to think about the patient's action at X2. Right. So if the patients are declined at XY, it makes
right.
decline at X2, so which make it even more complicated.
Yeah. Well, yeah. So yeah. Okay. Anyway, that's this kind of where we are now, and then so the problem is that we are interested in potential outcome essentially, right? We are not just interested in realized data, right? We are not really only interested in realized data. What we are really interested in comparing other options and try to come up with the best strategy possible, right? Best possible strategy. So that is the whole idea. So that means, so we have an outcome, I mean, decision, but this is potential outcome, right? So we have two concepts of potential outcomes, actually. This is more complicated because one is the potential outcome for Y. Okay, so Y is obtained end of the day. I mean, after all K visit, and then you will get final, cured or not cured, something like that, right? So, or if it in the reinforcement learning literature, it would be just a reward, some of the reward. So at each time you get some reward, and then Y is just the sum of the reward, or it could be something else. But sometimes we observe reward every visit. Okay, so like a number of clicks, something like that, right? So for some test. Okay, so in this case, outcome can be defined as a sum of the total reward. So that is, but the problem is that we don't really obtain all possible options. So that is a tricky part. in the HI infection example, the reward is I think CD4 is a kind of a count of the good blood, something like that, right? And so this is a kind of a good sign. So then basically we I think, I mean, I don't know the details, but this is one of the measurement for the reward.
Anything with a star in potential.
Potential, right. So interesting part is that here we have actually, in addition to potential outcome for Y, we also have a potential outcome for X. That is the tricky part. So potential information. So because we have basically we have given a sequence of A's, right? Given a sequence of A. If I choose different A, then my X will be changed, right? And so that becomes a very interesting problem. Actually, that is something called agent environment interactions. So agent is a doctor. Environment is patient. Something like that. I mean, in the DTR context. So agent choose an action. Doctor choose an action, right? Give a prescription. And then patient basically take this action and then next time the patient may show some progress or some changes. And also, so that is actually, so state is X and reward is a part of Y. You can see it, you can view it. Reward is actually the outcome. Okay.
I think the reward be included in the future X.
Yeah, you can view it that way too. But yeah, so I mean, so in some cases, yes, but in some cases, reward is a separating separate one from the state. So basically, state is kind of auxiliary variable, while reward is a specific to what we want to optimize, right? We want to optimize the expected reward, right? And so that is kind of so then you basically have a baseline X, and from the baseline X you have a this is actually through the action, right? And then using the action you update the environment will keep will use this one to give you another result, right? And then use that to update A. So this is kind of interaction type. And then, so I think this is, so this is kind of reinforcement learning setup. And our TTR is a special case of the reinforcement learning in some sense. Okay. So yeah. So once you understand the TTR, then you are in a position to expand your research to reinforcement learning in the future. Okay. Now, so potential outcome. I mean, the concept. So there's a lot of new concepts. So maybe it may take some time to get familiar with this new concept. But once you're familiar with this notation and concept, then the principle itself is not totally different from the single DTI. So okay, so the potential outcome is so X1 is not really potential, right? Because there's no. Sure.
So is S and R, what's the relation between S and R? Are they like
Dependent or?
Yeah, I mean, so this is R. So we really don't care about X specifically, right? Our goal is to optimize reward, total reward. But to optimize total reward, all I have to do is to choose the action, right? But I cannot really do anything directly with the reward. I need to use the information, auxiliary information, in order to do the modeling.
So they are dependent.
Yeah, sure. Yeah. So this is X and this is Y, essentially. Okay. I'm sorry. So environment is so this is kind of environment is a data. So environment gives me the data. Okay. So I observe this, and then I make a next decision.
If there is a doctor and a patient, and the patient has some kind of like cancer, and the doctor needs to give some kind of like design to the patient.
Right.
And probably the patient wants to like kind of the cancer cells in his inner of his body and to reduce, and the white blood cell and inner like or his body still maintain on the like high level. But the state of the patient probably can be like goes to very bad, which means the state of like the patient may be feel very sick as the design goes. And but you said you don't care about the state at all. Is that true in the real life?
No, I do care about the patient in practice, but I'm talking about the mechanism behind.
But I feel it's not very kind of practical in real life. In real life, in the same like this.
I think any complex decision should start with a simple formulation, right? So this is the starting point.
So state like in this design is totally like you don't care about this. You only
sorry?
care about the reward. It's kind of like you want to like maximum the reward, but you don't care about the state. Right?
The reward is the result, the problem given to me, right? Doctor. So whatever, I'm a doctor or whatever, or I'm a programmer, economist, or marketing. The task was given to me already. So the task was to maximize the reward. And how do you define the reward is probably well understood at the beginning of the job, right? So as a doctor, for example, the reward is, for example, for this kind of want to make sure that this this particular measurement is good, gives a good status, right? And so I don't know whether I answered your question. Okay.
This type of problem, the data is already given to us, right? So there is no need to consider explore some
Right.
So because if it's online learning, so we need to also think about explore some other.
I see. So that's another problem. I think that's another topic.
Okay, so
Right. Here, right here. I think the goal is to understand the mechanism for the potential outcomes, right? And from the data, so we don't really observe this one directly, right? We don't. There's something I plan to explain later, but maybe it's good idea to discuss it a little bit now. So yeah, this is really the key concept. What is this? This is the data. You have a data model, but you don't have a particular data model. Your model is in terms of the potential outcomes. So how you translate your potential outcome model to the data model is the key tool to translate the whole part of the DTR problem actually. So basically, see this Y star is a potential outcome. So that is a latent, right? So that you basically you need to this kind of you need to do this kind of a marginal density marginalization. But using the assumptions that you have and you see assumption, you can actually use conditional independence and Schutba. So using the Schutba assumption, you can actually express the density of Y given Y star and A as just a point mass jump, right? Because you know that Y is equal to Y star for that A, right? So you have a point mass. So you put it to here, right? You put it to here and recompute the whole density, joint density, then you end of the day, you can get this one.
So here the Y star is all the potential.
Right.
So then this also, if we need to work out this integration, we also need to know the correlation between potential outcomes.
Actually, no, because you know that you have only choose one of the two. Okay. So yeah, that's a good point. But turns out that if you given, for example, given A equal to 1, this integration out is over Y star 1. For A equals 0, this one will be over only Y star 0. So that's how.
There's never
Exactly. Right. Yeah. So, well, anyway, I'm gonna go come back to this part soon, but the key that is actually quite important concept. So basically, this is what we are interested in, right? So we are interested in characterizing the joint density of the possible potential outcomes. So because that is the nature, right? I mean, that is the nature of the environment, right? You want to know about your environment, but you don't have a direct observation of the environment. It's kind of distorted. You only have a kind of a distorted version of the environment data. So
the query is all the possible.
Right.
The set of all the possible actions.
Exactly. Right. So this is actually for any sequence, right? For any sequence that's feasible, you want to know, right? You want to see so that is for all, right? For all. So that is quite a difficult problem.
The definition of double star, we do not need to include the R, like the reward. There is only
actually here.
That is the final one.
Right, final one.
So we don't need to include.
Actually, so depends on the problem setup. So that's why I put the OR. So in some problem, you observe you have a specific reward for each data point, for each time point. Then you have this kind of potential outcome. Or some cases you have this kind of potential outcome structure. So that depends on your problem. Okay. And there's some additional concept to worry about. And so I'm going to briefly talk about this. So what feasible sets? So remember in this acute leukemia example, so we point, so basically the feasible so M1, M2, S1, So this choice basically depends on this response, right? So feasibility means so at decision 2, only maintenance option. So this is a maintenance option. While this is a salvage option, okay. So so if RE response is 1, then we have this one, right? And if R is 0, then we have this salvage option. So in this case, the feasible set, okay. So feasible set is a subset of options that depends on history. Okay. So formal spec is for any history at decision K, the set of feasible treatment options can be subset of the all possible options. Okay, I mean, this is just a concept. So, okay. So that is called the feasible set. I think that's just some details concept. So in this example, for example, so for example, in this previous example, if H2 history indicates response, then this is the only feasible option. So psi 2 is this set, and non-response psi 2 is actually this set. So that is the concept of the feasible set. Okay. So why we worry about this? Because the regime, right? The regime that we're gonna determine should be inside the feasible set, right? Should be chosen among within the feasible set. So that is the basically. So given the specified feasible sets, a regime whose rules select the treatment options for the history from those in the feasible set defined in terms of psi. So the regimes are psi specific, and the relevant classes of possible regime depends on psi. Okay. Okay, and psi specific regime. So the decision with historic HK returns only options in psi KH, which is a function of x bar k and a bar k minus 1. So that means TK need map only a subset of H2 AK. Okay. So now we are now in a position to define our problem. So this is so far we just introduced concepts and notation. Okay. At time K, DKHK returns only options in AK, right? And so now, so why we are repeating the same thing where previously we discussed the potential outcome for A. So okay, here, so potential outcome for a given A. Okay, now remember, so it's like this. So in chapter 3, right, we introduce this concept first, and then from this we introduce this concept, right, which is what, which is like a and then y star a. So it looks complicated, but it's nothing but just right, it is should, so it is nothing but the how the potential outcome would be for the rule, for the decision rule, right? Because potential outcome was originally defined only in terms of A. So then for a D, for D, then we need to derive, right? Derive potential outcome for respect to D from the potential outcome for A. So that is basically the idea. So potential outcome for a given regime D, we can conceptually derive the potential outcome on the regime D with this argument using the same concept, right? Same. So basically, this is what we just, so given the rule, right? Given the rule, we just choose the option, right? So given, so by the way, this D depends on, so this DK depends on the history at that time. So in that case, for time 2, the history is 1, right? So then basically it uses the x1. So given x1, given the rule, we know which A it chooses, right? So that you can basically find out the corresponding A1. By the way, I don't know whether this is really A1. Is it A1? Okay, right. Because it's a T1. Okay. So T1 is the rule that determines element options in script A1, right? Yeah, it's quite and same story here. T bar K minus 1, that is this one, which is uses. So this is potential outcome for X, right? This is potential outcome for X, and this is potential outcome for Y.
So the potential outcome for xk only depends on k minus 1. We don't need to take the summation of k minus q, k minus.
It's a bar.
It's a bar.
This bar means the whole
Okay.
from 1 to k minus 1. Yeah, right. Yeah. Yeah, I think the understanding the notation takes so many things going on. So anyway, why we define this? Because we want to eventually, so the goal is to find the optimal treatment regime, right? So that is the ultimate goal. And so to choose this, to do this job, right? To this job, we need to define what is the value, right? Value. So what is the expected value of the potential outcome with respect to D? So basically, this is what we want to optimize. So that's why we want to define this, right? So this one is defined this way. Okay.
Yeah. So the definition of Y star D.
Right.
Y star See, so, okay, so capital K is like the endpoint. Okay, so it depends on also the potential, the action. Also depends on potential action.
Right.
So it's, the evaluation must be.
Right.
complicated.
Yeah, that's right. Okay. Okay, so that is the goal. So now, so to achieve the goal, we need to start from the data, right? From what we have. What we have is the data. So the data is this. So the data is the IID observations of the X bar I, A bar I, and YI. So what is the A bar? A bar is so this is a random variable, but realized, right? Realized random variable. So AK is the fifth option actually received at decision K. And then this is the not the potential, right? So this is the realized. So realized auxiliary information at decision K. So or to be rigorous, it is in the textbook it says it uses the term of the intervening information, basically auxiliary information. Okay, at time T, at time K. And then this is the final one that you want to optimize. So the observed outcome after decision K. So that is the data. Now the natural question. So here's the problem. Okay. So the problem is that recall that our goal is to estimate the optimal decision from the data. To do this for any fixed D, for any fixed rule, we must be able to identify from the distribution of the potential identify the distribution of the potential outcome, which is this one, from the distribution of the observed data. So so remember this, what is this W star? Let's go all the way back to here, right? So this is the all possible potential outcomes. So X1 is not really the potential outcome. X1 is you observe, right? X1 is observed, but X2 depends on A1. So that's why it becomes a potential outcome from X2. So from X2 to XK and then Y star. Okay. So that is the okay. But for at least for K equal 1, right? For K equal 1, we already know how to do that, right? That's the main contents of the chapter 3. The 3 assumptions, right? SUBA and NUC and positivity assumption. These 3 assumptions are actually identification assumptions, right? So identification, what do you mean by that? Identification of the potential outcomes, right? So distribution of the potential outcome from the observation, right? From the observation. So we'll basically need the same 3 assumptions, the same set of the 3 assumptions, but because we have a sequential nature, so maybe the context is a little bit different. Okay.
So like a little bit confused about the definition of the D. Can you just
yeah, sure.
The small d?
Small d, okay.
The decision function. The definition of the.
I guess yeah. So this is the
Right. So based on edge, right? So based on the historical,
Right.
right? So then in the derivation you just mentioned, the D also depends on potential responses. So the D should just depends on,
No, this should depends on history.
yeah, the history, but the history is different from potential action, right? So if you go,
Let's be
take on a little bit.
Well, okay. Treatment option depends on history and information treatment. So
So when you talking about the potential responses and potential action, you can move down, yeah, move down again. And move down. Yeah, so here, so the D actually in the indicator, it depends on the potential action.
right. That's right.
Yeah, but I think the D should only depends on the history.
Well, actually, the sequential ignorability assumption. So we'll talk about that, but no matter how basically you observe this. So basically, the point is that it doesn't really matter how you obtain A, as long as you have the A. I mean, so yeah, that is a tricky point, but yeah, I think this definition is all in terms of the potential outcome, right?
Yeah.
But we'll actually basically the whole idea is how you is. So let me let me. So this is something like that. So end of the day, what we'll kind of show is something like this. So basically, your conditional distribution in terms of the potential outcome turns out to be same as the conditional expectation of the realized given. So using the potential outcome for that A, if you can actually have that A in the data, no problem. Something like that. Yeah. So that is that's the whole idea of the identification, how you can really characterize. Yeah, actually, that is actually quite important. So that's, I didn't, that, so because you brought up, oh, okay. No, not this one, DTR. So actually, this is the next week. But so just a preview. I only made the 6 pages for the next. But so here's the observation. Okay, and potential outcome is this, right? And the goal is to identify the distribution of the potential outcome on the NED from the distribution of the observed data. So that is the real key identification problem. And that is the James Robbins. So 1968 key paper basically figured out how to solve this. So that is the famous G formula. And so the whole idea is, so the idea is this one is a joint distribution of the potential outcome, right? But this one is a factorization based on the observed data. And that is very actually interesting. But I have a, so basically, so here's an illustration. In k equal 2, you have 3 random variables, x1, x2 star, y2 star, right? And so you are interested in finding this joint this density. And which is this one, right? Which is as a function of potential outcome. This is, you have a marginal, conditional, and conditional, right? So it's just a very simple, you know. And then the key point is that under the 3 identifying assumptions, your conditional distribution is actually expressed in terms of the data. So this is a potential outcome, while this is your observed data, observed random variable. Okay. Same thing here. So that is actually the, so all that is the key idea. And once you do that, then how you, so this one, once you establish this, then estimating the parameter in this conditional distribution is easy, right? Because you have a data already. And here, same thing. So basically that is, that's the idea, but I will cover that further. So anyway, so yeah, so basically, this is, I will explain. So I covered this a little bit, but let's be more rigorous, because this is conceptually quite, I think, quite important. So basically, this could be a, so actually we have 2 equations, right? This one is either this one or this one, right? So it could be, so we can actually have the same, but star 0, A. So we can integrate out over y star 1 or y star 0 either way, right? But what matters is depends on what you observe, right? So what you have given in A. So, but anyway, first of all, you get this one, right? And this part I already explained. This part I already explained, right? And now let's be very careful on how you actually compute it. So that means, so, okay. And so this could be, by the way, this A, we know that A can be either 0 or 1, right? So if A is 1, right? If A is 1, that means this is given A equal 1, right? Given A equal 1, so then we can use the first one. And then basically that will be, so if you plug in this guy to here and compute the integration over y star equal to 1, right? Then you just, all you have to do is replace y star, right, by y, and then you factorize. So you have basically this guy. So this, you have this guy times this guy, because you have a factorization. Same story here, right? Same story here. You now, the density, it will be the second density, so that you will have F0 given X. Okay. So so that's for a single DTR. But now we are talking about the general multiple. So in that case, so Stuba, we need Stuba condition, of course. So Stuart condition is that your xk. So this is your observation, right? Your observation is a potential outcome. So you basically, if you know potential outcome and A, then you know observe the random variable, right? So that Stuart is not really, it's just the consistency condition. So second one, so that is actually a multiple version of the NUC. So NUC is what? Conditional independence of Y star of A given X, right? So NUC was this, right? Conditional independence of this. And now sequential randomization assumption is basically you replace by W star potential outcome. So your potential outcome is independent of the treatment effect given given the current decision, given the current history.
Wouldn't the WK
Actually,
because the futures depends on it.
no, the future doesn't depend on your choice. Potential outcome is fixed, right? Your choice depends on which one you observe, right? But the potential outcome itself is already fixed.
But this is requires the full set of W independent of AK.
Right.
Not W.
I see. You're right. I think there's a weaker version of this condition, but that is not really critical for the discussion. Okay. So that is a sequential randomization assumption, which is basically conditional independence. So it implies that all accrued information used to make decisions is captured in the observed data. Okay. So that is a strong assumption, but that is kind of missing a random type assumption. And positivity assumption means that you need some sequentially, right? Sequentially some positivity. So all treatment options in the feasible sets must be represented in the observed data. So there must be individuals in the data who receive each options in psi k each k. Let's use the example so remember in decision one, right? Decision one, we already understand this positivity assumption already. Basically, but this is more formal type. So gamma 1 is defined to be the all possible realization of the baseline information with the support.
So this only assuming positivity, not strict positivity, right? It's just does not require like to sum away from zero. It's just not a zero.
Yeah. Well, what do you mean by strict positivity? This is a strict positivity.
It's not the same, not than zero for any x. Because if we just assume it's not than zero, it could be like for some x, it could be very close to zero.
Okay. So basically, this is the positivity assumption for decision one.
Right. Okay. I think it's should doesn't matter for identification.
Okay.
But it matters for estimation.
I see. Okay. So basically, this is what we want to claim, right? But to be more rigorous, what we want to clarify what is a relevant set to define this probability, conditional probability. So then this history should be should be in the set of, so this is the set of history, and then A is in the plus, in the what, in the options, is it called the plausible, or what is the terminology? Feasible set. Okay. Yeah, so many. Okay. And decision two, the history. So the tau two, I mean the gamma two is the set of a possible history where this probability of this the probability of this particular history should be positive. I think this is just to make the formal, you know, the formality to make the argument clear. The textbook uses this kind of notation, but the concept is basically we don't want to include impossible histories, right, to our decision sequence, something like that. So basically this is, so gamma 2 and lambda 2. So, and then generally gamma k and lambda k, where gamma k is the history, possible history, and lambda k is the history and the feasible set, okay, for that history. Okay. So that is basically one of the important result is that okay. So under this assumption, we can basically show that this, I already explained this a little bit. So basically the conditional probability of the outcome, potential outcome, can be expressed in terms of the realized outcome, given the realized value of A for that potential outcome. And so using that, the tau, I mean gamma k, can be expressed in terms of the potential outcomes. And this proof of this equality will be covered in the next. I mean, this is the part of the G formula that I'm going to explain next week, but I didn't cover it today.
Do you have a question about the productivity if we go back?
Yeah, sure.
Yeah, so here. So given history, right?
Right.
So given history, we should have an optimal decision. Right? But this productivity says that the probability of taking any decision is not than zero. So basically, so it means that it will not take the optimal.
Right here, this is the all possible options, right? And then we use this potential outcome. So our goal is to find the optimal decision using the value.
I mean, the data they have is not optimized
Right.
in terms of the decision.
Right.
Yeah, because if it's optimized, probably the possibility, sorry,
I see.
the productivity assumption may not hold, because if we just choose the optimal decisions, then the other A will be probability zero.
I see your point. Well, right. So that is a little bit
optimal decision may not be equivalent to the optimal decision after the offset.
So, well, actually, so I mean, that's probably we are talking of the same thing. Optimal decision has nothing to do with your observations in some sense. If you, right, it has nothing to do with your choice of A. Because it's all function of the potential outcomes. Right? So if you know the potential outcome distribution somehow, then you know the best decision already. So then how you, and then you of course want to find the optimal decision based on the rule, but this is more about the assumption about your realized value of A, right? So you think that we believe that this realized the data, right? This is more about our data. Our data contains all possible options sequentially in some sense. I don't know that. So that is kind of assumption to make an estimation possible. So I think this is, I'd say, I have a data, right? I have data and I want to, so I know that my data is really reflect the environment directly, but I have some weak assumptions, some kind of assumptions that that make me to make an inference about the environment under that assumption.
What's the ignorability is talking about?
I'm sorry?
I think that is what the ignorability is talking about.
Right.
Our potential outcome is independent of the action. So, in the data, there's the action has nothing to do with the so-called optimal.
So yeah, so ignorability is in some sense already implies, right? Implies.
Ignorability says given T, given before T. So I think ignorability does not contradict with the optimal treatment choice, because optimal treatment choice is given information of T minus one before T. So that is also the ignorability talking about, given the information of T minus one and before. So it's ignorable. And then if you choose based on the optimal treatment, you still based on the information given T minus one and before.
Okay.
So ignorability means, yeah, I think the positivity is
I see. Yeah. So actually, and now I think that I can see what's the real difference between the reinforcement learning and our problem. In the reinforcement learning, we sequentially observe so that we are actually in control of the next observation.
right.
But in our context, in our problem, actually we treat the data is already given externally. So the data collected, whoever make the decision have no idea about the optimal rule at all in the beginning. And so that's just a kind of a external data that I want to use to make a decision. While in the reinforcement learning, I'm smart, right? I mean, the agent is smart enough to do best decision as much as it can while learning, right? And so the context is somewhat different.
I think in reinforcement learning, so that's also we need to explore.
Right,
Right.
I
So
see.
even
Sure.
if we know the best,
Still,
we still need to use the non-optimal action because
Okay.
we need to learn.
That's right.
When we need to learn, they need to explore.
That's right.
So it's kind of a combination of learning and optimization.
Okay. That's right. Yeah. Okay, I think that's all.
That's last page.
Okay, you have a answer question? No problem.
Last page.
This one?
Yeah.
Okay. You mean this one?
Yeah.
Oh, I didn't. Oh, wait. Okay, sorry. Okay. So, well, So this is using this gamma k, we can make a more precise definition of the regime as follows. So the regime, the precise specific regime is that it gives a, so for every, so I think we now have a more specific definition of history. The history should be, it's not just a vague whole possible history, rather it's a history of positivity, satisfying the sequential positivity condition. And then and then for that, this regime can be defined. Okay, so this is the one, and then so like a tau k to psi k. So previously it was like a history, right? So this is more vague. Okay, this is much wider, but this is more specific because we narrow down the feasible from the positivity, right? Possible history, from the possible history to the feasible set. Okay, I think that's all.
Thank you,